in Florida. It needs to be protected. How many of you have seen a well-used car with cracks in the dashboard? Okay. So to avoid it, you avoid exposure to UV light. Lubrication properties can be affected for better processing, like sodium stearate. And I'm going to show you the processing routes. Also for aesthetics, some dyes and pigments are added to change the color of the polymer. And for specific applications, there could be flame retardants. If you buy a pillow, by law, you're commanded to stop talking. Yeah, the flame retardants. They're all extra chemicals that are added to the fiber, which we will talk about as well. Okay, this is important, guys. Do you recycle? Yes? What do you recycle? Because I think we're going to cover this topic in the end. But all plastics are classified into the thermoplastics and thermosets. And thermoplastics can be recycled. Polyethylene, polypropylene, polystyrene. Thermosets are not. They just simply degrade when they're heated. So by the way, this process of recycling involves some sort of heating. And the examples are urethane and epoxy. Epoxy is typically two-component, and once there's a chemical reaction that the two components undergo, typically a hardening agent, it cannot be reused or recycled. Let's consider processing. To control the process, to control the structure, to control the properties. So anything that you see around you has a certain physical shape. And here's an example of compression molding. Here's the tool which has the mold base and a plunger, which is hydraulic. And once you add the polymer here, you kind of like bring it together. So once you bring it together, there's going to be a gap. And this is used for high throughput manufacturing. Another process is called injection molding, and it can be applied to both thermoplastics and the thermosets. Here is a ram which applies hydraulic pressure, and there's a feed hopper that has your raw material, and it pushes it into a barrel. Eventually, all of that goes to a heating chamber. And there's some sort of a spreader that mixes this stuff. And the temperature is raised to the point where it becomes liquid. And under pressure, it's injected into the mold cavity. And it assumes the shape of the mold. Again, this is heavily specialized equipment. Guys, I can see who's talking. I mean, it should be just me talking, unless you have something to say. What do you have? And all of this needs to be cleaned out properly. So, how many of you have ever used a meat grinder? Have you ever used a meat grinder? Or it's a general term of a meat grinder. But there is turning screw. You see that? This turning screw transports the material. And this is primarily used for extrusion of thermoplastics. You have plastic pellets, that's your incoming material, and they are melted, and this screw is turning, and while it is turning, it is pushing the material, which there's some sort of a heater. The grinder for food processing typically does not have a heater. And then the plastic gets into the liquid state, and it gets extruded. For something like this, it has to be a continuous operation that runs 24/7. It's not like you can just stop from one shift to the other, which is why most of the processing happens 24/7. So there are different shifts. Before joining USF, I worked at Motorola in Phoenix and Texas, in Arizona and Texas. And as part of my job was to inspect some of the product, and you put a stop on a lot. I brought a wafer today, so I'll, when we talk about semiconductor manufacturing, I'll bring it to the actual moment. And then in the middle of the night, you have a pager going off or a phone call saying, your lot is here, do you want me to stop it or do you want me to proceed? So the problem with that, with the continuous manufacturing is that, it does not necessarily coincide with the normal schedule of a regular person, that most of us sleep at night. You can go to Lowe's or Home Depot and you can buy a plastic film. And when you buy it, typically comes at a certain width, you would realize that it is consisting of the two layers. And I bought it back in the day when I was laying down laminate flooring in the house to put it down as a moisture barrier. And the reason there are two layers is because of how it is manufactured. From this extrudent here, you see that it goes up and there's air that is supplied. So essentially you're like blowing a balloon while, so this is the blown film with an air bubble that gets rolled. And once it gets rolled, you can see that the cross section is circled and then it gets collapsed like this. That's why there are two layers. And then it's just easier to sell it this way as a two-layer product. And then it depends like how thick it is, but this is the processing for the blown film extrusion. And again, it is a continuous process. Once it goes to steady state, they just produce large amounts, and then eventually it goes through the pinch rolls, and over here the temperatures drop down and it's going into a roll. And then at a certain point, this gets cut and the operation just continuously blown in the film. There's a special type of polymers called fibers. And for fibers, one of the requirements is that the length to the diameter ratio is greater than 100. And it's very often used in textiles. I mean, look at that. Nowadays, I don't know, the science becomes political, but here is a process of getting the fiber from the melt. And then the fiber gets, through wet spinning, this is the cross section of the fiber. the idea is that the fiber has to have a cylindrical shape with a circular cross section, but sometimes it goes into this bean shape like this, and it's a defect. So the difference in the processing was in the warm bath versus the cold bath. So the fiber goes into liquid, into water. All right, and apparently it affects the percolation threshold. That's the scientific term for that. And here is the solvent, polymer, and non-solvent. And the diagram shows the difference between binodal versus spinodal decomposition. If you ever get involved in research, my advice to you is that you must have a lab notebook to document everything what you're doing in terms of the experiments, because and this was published in Thermokinetica Acta. The reviewers asked to do more experiments, but I did not have the setup. So there is no way to repeat those experiments, and at that point you just say, well, we cannot repeat those experiments because either the starting material or the samples or the equipment is no longer available, there's no access to it. So the fibers typically have very high tensile strength, and they also have high degree of crystallinity. Extruded polymer goes through a spinneret, which is a die containing many small orifices. And these fibers are drawn under tension. So as a result, there's fibular structure. And if you ever buy, what's the name? Fishing, it's not fiber, fishing line. That's how it's made. Artificial fibers are also used for making weaved clothing. Okay, any questions about fibers? This stencil machine is perfect for testing the mechanical properties of fibers. And the device is very simple. Most of the parts are from Alibaba, from China. There's a power supply, and here's the stress tensor, and a stepper motor right here. And we've tested human hair. Let's see which one is human hair. Oh, here's 16 microns fishing line is C, right here. This is a fishing line. And then E is human hair. Do you see the similarity between the two? Human hair can withstand very high strains before they actually fracture. You see like 10% strain. and more, so this is the first cycle, this is the second cycle, third. So every time, and the same thing for the fishing line, every time you test it, it becomes longer. So it's stretching, and it is stretching without failure. This is the most important part. And the fishing line is rated for what? When you have, how many of you fish? Ever fish? No, nobody ever fish? Okay. So what's your fishing line? How do you buy a fishing line? Based on what criteria? Okay, so when you go to the store, you're going for a certain specific kind of fish, right? And it has the maximum weight it can hold before snapping. Okay, so this is your criteria, and obviously the thicker the fishing line, the more weight it can support. I have a friend who is fishing for sharks off the shore, and it takes him about an hour to pull out like a 6+ foot long shark. He releases them, but he has a special fishing line. What's the name of the fishing line that you use for like really heavy fish? You got the material. It's weaved. It's typically green color. Braided nylon. That's what it is. Braided nylon for the very high strength applications. Okay, coatings as a huge industry, from anything from paint to varnishes, and in a couple of chapters we're going to be talking about corrosion and degradation. PPG is producing a whole bunch of specialized paints. It can be also decorated for improving the appearance, color. It can also be used as a electrical insulation. The big ones are glues that can bond two materials together. They're called adherents. And there are two types of principles that they are operating on, either on the secondary van der Waals forces or mechanical, where they penetrate into the pores and crevices and provide the bond. So there's a special adhesive for bonding metal, for bonding wood, for bonding plastics, and they operate on different mechanisms. Films are produced by film extrusion or blown film extrusion, the example that I showed you. And it is also possible to make foams where the bubbles are incorporated into the plastics. So all of that provides a functionalization of the material in terms of the specific applications. And then there are advanced polymers. Remember, we started this class by looking at an example of a hip implant. This is the ultra high molecular weight polyethylene, UHMWPE. And this is the molecular weight, 4 million grams per mole. And the idea is that it would be a self-lubricating surface, which allegedly should never be replaced. You know, this is the worst case scenario. Unfortunately, most of those hip implants are nowadays can withstand about 20 years, after which they have to be replaced. So when the person is young, they can undergo the surgery, but in 20 years, it becomes harder and harder. So not only this material has high impact strength, it is also highly resistant to wear and abrasion. You cannot generate debris particles. I personally know a person that had a hip implant, and unfortunately less than a year later they died because the debris from the implant went in and blocked the heart. And that was determined to be the reason for death. But here the idea is to have low coefficient of friction, a self-lubricating surface, and more importantly is not generating any debris, because it wouldn't be a good thing. Other advanced applications would be bulletproof vests, golf ball covers, and for the hip implants, acetabular cup. Here's an example of styrene butadiene block copolymer. This is a thermoplastic elastomer. Here's the butadiene, and this is the soft component that will give you unique mechanical properties. So, in the end, the limits of using plastics and polymers is typically lower elastic modulus, lower yield strength, lower fracture toughness, and lower temperatures of application. Very often, the deformation is time and temperature dependent. Thermoplastics have small elastic modulus, yield strength, application temperature, but higher fracture toughness. They are also easily can be formed and recycled. The rubbers have large reversible strains. Thermosets have higher mechanical properties but smaller toughness. So this is the rubber. You can see how much it can be stretched. There is no similar material that can withstand so much deformation that you can physically see. Normally, when you are dealing with strains, those strains are very small. And we looked in the processing of plastics in terms of the compression or injection molding, extrusion, film blow, the melting and glass transformation temperatures, and polymer applications as elastomers, coatings, films, fibers, adhesive foams, and advanced polymers. I want to again emphasize this. Some of this material is overview, but this is super important. I told you about this experience I had when I worked at Motorola, when the supplier, which was Dow Chemical, changed the formulation of the plastic for packaging of chips for Mercedes and Ford. And they started to fail high temperature tests. Back in the day, strained silicon was a big deal. And when I worked at Motorola, I did X-ray diffraction, and the idea was to deposit a silicon layer on top of silicon germanium. And there's a process called epitaxy. And the idea is that if these are the atoms of the substrate and these are the atoms of the film that go on top, if you stretch the substrate a little bit, like maybe maximum to 20%, then epitaxial means that the atoms would go on top of the other atoms like this. So if this one is stretched by adding germanium, then there would be what's called silicon cap. And they were able, AMD was one of the first companies to introduce this technology. You can read about it. They increased the operating frequency of the processor by about 20%. But that process involves changing the band gap of the semiconductor. So what happened is, please take a look at this again. If we allow the polymer to be slowly cooled, then at this point it would undergo crystallization. Okay, and either form a semi-crystalline solid or a crystalline solid, meaning that there's a gap in the specific volume of the material. But if we do it very fast, then there's a slope change. There's no discontinuity in the volume. So please keep this in mind. And this characteristic temperature is called glass transition temperature. Any questions about plastics and polymers? Because we only discussed three: metals, ceramics, and plastics or polymers. And then the fourth class depends on who you talk to. If you talk to can you live without your cell phone or your laptop? Digital detox. Can you survive in the modern world without a device that you carry on you 24/7? You sure? So some people say that silicon and semiconductors is another class of materials. Or some can argue that composites is another type of material. So let's talk about that. We're going to talk about the classes of composites and the types of composites and the advantages of composites compared to regular materials, and also very importantly how we can predict the properties of these materials depending on their type. By definition, composite is a combination of two or more individual materials. And the goal is to obtain desirable combination of properties based on the principle of combined action. Like, for example, low density and high strength. My master's thesis was in aluminum matrix boron fiber composites. And they were used to produce satellite structures that have the strength of steel and the density of aluminum. Boron by itself is very brittle, and aluminum is very ductile. So the idea is to combine very dissimilar materials to obtain certain properties. We're going to talk about artificially made materials, where they're multi-phase materials that are made by a human. Okay? Because there are some naturally occurring composite materials, such as wood, the oldest one that were used by humanity. And what was the first airplane made from? The Wright brothers? Do you know? Have you been to DC? Have you seen that first plane? No? You never watched the documentary about the airplane? The Wright brothers, what was their business before they started to make airplanes? Bicycles. Okay, so they had the technology to make stuff. Okay? Brothers, and where's Wikipedia? And we can look at a whole bunch of images. So, what is this plane made of? You think? Yeah, wood and fabric. So the idea is to make something that is very light. If you are ever in a Airspace Museum in Washington, D.C., it's super interesting. It's part of the Smithsonian Museums. There's another airplane that is powered by a human, like a bicycle. Okay, let's define those phases types. One is the matrix. And the matrix means that it is a continuous phase. And the second phase is dispersed. And this phase is discontinuous and it's surrounded by the matrix. So here's an example. This is the dispersed phase, and this is the matrix phase. You see that? That is the idea for a composite. Okay. What are the three classes of materials? Metals, ceramics, and polymers. And the same way composites are classified as metal matrix composites, MMC, or ceramic matrix composites, or polymer matrix composites. They're shown over here. And the matrix phase serves two major functions. One is transfer the stress to the dispersed phase. And the other one is protect that phase from. Let's consider, depending on the type of the composite, the function of the dispersed phase, the purpose of the dispersed phase. In metal matrix composite, the idea is to increase the yield strength and tensile strength and the creep resistance. What are the problems with ceramic materials in terms of its mechanical response? Ceramics are brittle. So the main function to make a ceramics matrix composite is to increase the fracture toughness. And for polymer matrix composite is to increase the elastic modulus, yield strength, tensile strength, creep resistance. So the types can be either particle, fiber, or structural. The first phase can be in the form of a particle, or particles that are dispersed within the matrix. Or it can be fibers. We just finished the polymers picture, they're fibers. Or it can be structural. Here is an example of woven fibers, and this is the top view, and this is the cross-sectional view. Those little tiny pieces here, those are fibers that are weaved, and then all of this goes into some sort of a matrix. Composites are classified into particle reinforced, fiber reinforced, structural, and nano. Particle reinforced are classified as large particle or dispersion strength. Fiber reinforced can be continuous aligned or discontinuous and short. Discontinuous short can be either aligned or randomly oriented. And in terms of structural, there are two types, laminates and sandwich panels. Let's take a look at particle reinforced. Spheroidite and steel. Here's the ferrite alpha matrix and the iron 3C particles. So we have a distribution of brittle particles within the ductile matrix. Or tungsten carbide, cobalt carbide, where there's the cobalt matrix, which is ductile and tough, and tungsten carbide particles that are very brittle and very hard. And the rubber tires that you're driving to school. Here's the rubber matrix, and the filler is the carbon black, which is stiff. That's the reason why the tires have this color, is because of the filler that is carbon black. And then depending on the ratio of the rubber matrix versus the amount of carbon black, these tires can be stiff or these tires could be soft, and those properties affect the traction between the tire and the pavement. And typically for higher performance, there are softer tires that are used, which have more rubber and less carbon black. But then you would have to change those tires because they wear out fast. You know. How many miles do you get out of your tires typically? Well, it depends how you drive and what you're driving. But roughly, like, most of the tires are rated for how many miles? 50,000? Yes? Have you ever been able to get 50,000 miles out of tires that... So 50,000 miles on an average use of a car would be about 5 years. Have you ever changed tires? You never changed tires? Okay, well, it's going to be part of normal life. American is to change tires once in a while. Unless you are, I don't know, if you're leasing a car for 3 years, maybe you will not have to change the tires. But if you're keeping the car for longer than that, then about 5 years you'll have to change the tires, maybe less. So the question is, let's say you buy the car. When you buy the car, you do not have control of what tires come with the car, right? So whatever the manufacturer of the tires puts on the car, that's what you get. Or if you buy it used from a third party or from a dealer or whatever, it typically comes with the tires, right? You don't have to change the tires right away. Sometimes you do, but most of the time you don't. So then the question becomes, how do you choose the tires? What are the criteria? Yes?
You gotta see what weather the tires are made for. So do you want all season or summers or winter?
That's a very good comment, because if you're going to be ever in Minneapolis in the winter time, the wind chill factor temperature is minus 50 degrees, and the tires can blow because it's so cold. That's a very important factor. Actually, tires themselves are a composite because the tires have metal cord inside. So the tire itself is a composite because it has rubber and carbon black as a filler, and on top of that you have the metal cord that is inside the tire. Okay. Another example is concrete, which is a mix of gravel, sand, cement, and water. Why sand? Because it fills the voids between the gravel particles. So it's a multi-dispersed, multi-size system. And then there is reinforced concrete, which is reinforced by the steel bar or a mesh. What's the idea? Ceramic materials are 10 to 15 times stronger in compression or tension. Yes, they're 10 to 15 times stronger in compression. So what happens if we, all of you civil engineers, if you subject concrete to tension, it cannot withstand tension. It would crack. So if you look at any structure that has a door or a window, there is a beam, and the beam is reinforced with rebar. So whenever you have tension, you have metal that is subject to tension. Pre-stressed concrete. So here's the idea. You take the rebar and you can put it in tension, and as a result, the concrete is going to be under compression. Cracks do not propagate in compression. The other example is post-tensioning. Is after you made the composite, you use a threaded rod to apply compression to the structure. For the next semester in the fall, I think I'm scheduled to teach fracture mechanics. But it's kind of intuitive that the cracks do not propagate in compression. They only propagate in tension. Remember we talked about tempered glass, where the surface is put as in compression? Let's take a look at how properties are affected in terms of the elastic modulus. So we're going to use the rule of mixture that would allow us to do the calculations of the two extremes. The upper limit of the elastic modulus of the composite is equal to the volume fraction of the matrix times the elastic modulus of the matrix, plus the volume fraction of the fiber times the elastic modulus of the fiber. And this is a straight line that you see over here. The lower limit is 1 divided by the elastic modulus of the composite is equal to the volume fraction of the matrix divided by the elastic modulus of the matrix plus the volume fraction of the fiber divided by the elastic modulus of the fiber. And it is, as you can see, it's nonlinear. And it is this blue curve over here. This is the data for copper matrix tungsten particles composites, and it can see that the actual data is somewhere in between. These models are useful because they give us the upper and lower bound for the prediction of the composite. Because it is very time consuming, and it's an expensive process to manufacture a composite, to test it. The same idea can be applied for estimating other properties such as electrical conductivity or thermal conductivity. And what you do for this equations, you replace elastic modulus with the electrical conductivity sigma or the thermal conductivity K. Fibers. As we learned today in polymers, fibers are typically very strong in tension. And we can take, for example, fiberglass that would have very high strength and stiffness. And if we embed fiberglass into the polymer matrix, the polymer is going to hold those fibers together. It would protect their surface because the surface is very sensitive. That's where the defects are, and it would allow to transfer the load from the matrix to the fibers. Fibers can be in the form of whiskers, which are thin single crystals that have large length to diameter ratio. Examples are graphite, silicon nitride, silicon carbide. Because they are single crystals, they are very strong. And the other problem is that they are expensive and it's hard to disperse them because this fibers tend to agglomerate and form clusters. So to disperse them in the matrix is not an easy process. These fibers can be, the other type of fibers are fibers, which can be either polycrystalline or amorphous, and it can be either polymers or ceramics, alumina, aramid, e-glass, boron, ultra high density polyethylene. And finally, they can be in the form of the wire, like steel, molybdenum, or tungsten. And the question is, how do you differentiate between the fiber and the wire? And it's based on the diameter. So at a certain point, anything that's comparable to human hair, which is roughly 50 microns, is still a thin wire. And then it transfers to the fiber. Here's an example of continuously aligned fibers, discontinuously aligned fibers, and random. Can you tell me the difference between continuous and discontinuous? Looking at these two schematics. If I draw a horizontal line here, you see here that there is a substantial overlap between the length of the fibers, whereas here there is no overlap or it is minimal. Like on average, it does not expand as much. This is the difference between continuous and discontinuous, and these are aligned and these are random. So there's no preferred orientation of the fibers. And who controls this? How they're made? A process engineer to attain certain properties. Aligned continuous fibers. Metal in nickel 3 aluminum in alpha molybdenum by eutectic solidification. So here's a matrix, and these are the fibers. The matrix is ductile and the fibers are brittle. Here is a fracture surface of the glass with silicon carbide fibers that formed by glass slurry. The elastic modulus of glass is 76 gigapascals. The elastic modulus of silicon carbide is 400 gigapascals. It's pushing up there to a very high value. Example of discontinuous fibers, 2 dimensions. Carbon fibers are very strong. Carbon matrix is less stiff and less strong. So we have carbon fiber and the carbon matrix. They can be embedded into the polymer resin matrix, which is pyrolyzed at 2500 degrees C. And the main use is for the disc brakes, for gas turbine exhaust flaps, and missile cones, because of the high temperature applications. This is the distribution of the fibers in the plane, and this can be either discontinuous, random, 3D, discontinuous, or aligned. So the third dimension comes into play when it comes down to the orientation. Let us consider a very important technological parameter, which is the fiber length. And the idea is to increase the strength. So if the fiber length is greater than sigma d over 2 tau sub c, where sigma f is the ultimate tensile strength of the fiber, d is the fiber diameter, and tau sub c is the shear strength of the fiber matrix interface. And typically it's arbitrary. So if the fiber length is greater than 15 millimeters, then you would have the strengthening effect. So there's a better, here the stress is applied horizontally, and you can see that this fiber is bonded to the matrix here. So this effect is, for the long fibers, is when this ratio, the fiber length is greater than the strength of the fiber times its diameter divided by the shear stress. The shear stress would be the amount of stress that would be required to take single fiber and shear it in the matrix, like this. Because the fiber is bonded to the matrix, so you're not allowed to do this. And if you do, then it's a failure. So here you have low fiber efficiency because the fiber is just not long enough, whereas here you have higher fiber efficiency because the fiber is long enough and it does a very good job of transfer of the stress from the matrix to the fiber. And that's how we attain the reinforcement effect. I do have a paper about synthesis and characterization of nylon modified yttrium hydroxide nanocomposites. We'll talk about nanocomposites, but here you can see the distribution of this fibers, which are on the order of 1 micron, that were embedded into the nylon. This is the cross section. This is a plot that shows impact strength. You remember this Sharpie impact tester that I showed you? It's basically like a hammer. You set it up to a certain height and you let go, and the potential energy of that hammer goes into the kinetic energy, and then it impacts the sample, and after the sample is broken it continues to a certain angle, and that angle determines what's called toughness, or in this case we looked at the impact strength as the amount of modified yttrium hydroxide in weight percent. So you see here the about 0.35 gives you the highest impact strength, but what it also does is it drops down the tensile strength. So here is an example of the optimization based on the two mechanical properties, the impact strength and the tensile strength. And the other parameter was, in this case, water absorption. So the problem is the more fibers you add, well, actually this is good. The lower moisture absorption is good. But the tensile strength goes down. There's some good systems where we just take one parameter and it affects the properties in a good way that we're looking at. But here you can see the impact strength this is the optimal, and over here in terms of the tensile strength, it's better not to add anything at all. Let us consider some models that we can use for modeling longitudinal loading of the continuous fiber and estimate the modulus of elasticity for continuous fibers. This is the longitudinal strain, and the key here is this, and that's why it's called isostrain. Let's say I take, this is a piece of rubber, okay, and I take another piece of rubber that's, for this illustration, we're going to assume that these are two different rubbers, and I stretch it. You see? Both rubbers are subjected to the same strain. So when the fibers are aligned along the length of your composite, the matrix and the fiber are going to be deformed to the same amount of deformation, which is the same strain. Does everybody understand that? Okay, so the condition for the isostrain means that the strain of the overall composite is equal to the strain in the matrix is equal to the strain in the fiber. And then we can write the equation for the composite elastic modulus when the fibers are aligned longitudinal to the axis of the applied load. Okay, another example is we are subjecting our composite to isostress. The fibers are in this direction, and what we're doing is we are deforming it in the perpendicular direction. That means because the fiber and the matrix are having different elastic modulus, they would have different amount of deformation in them. And they're going to be under what we call isostress. So the stress of the composite is going to be equal to the stress of the matrix, going to be equal to the stress of the fiber. And based on this, the composite strain is equal to the strain of the matrix times the volume fraction of the matrix plus the strain in the fiber times the volume fraction of the fiber. That's where this equation comes from, where 1 divided by the elastic modulus of the composite is equal to the volume fraction of the matrix over the elastic modulus of the matrix plus the volume fraction of the fiber divided by the elastic modulus of the fiber. So from this, we can solve for transverse elastic modulus, which is equal to the modulus of the matrix times modulus of the fiber divided by the volume fraction of the matrix times elastic modulus of the fiber plus the volume fraction of the fiber times the elastic modulus of the matrix. And this gives us these two approaches here as the upper limit versus the lower limit, depending on how the fibers are oriented. But it has very explicit explanation in terms of either strain or either stress. And that changes if the fibers are aligned along the direction of the applied load versus when they're perpendicular to the direction of the applied load. Okay? And as a result, we can also make an estimation for the discontinuous fibers, which would be valid when the fiber length is less than 15 times the strength of the fibers times their diameter over the shear stress. And then what we can do is we can modify this equation by adding a efficiency factor. So the equation is the same, but if the fibers are aligned, this factor is equal to 1. If they are aligned perpendicular, then this K is equal to 0, so there's no effect on the fibers at all. They are not affecting the performance of the composite. If we have random 2D that is 3/8 for 2D isotropic, or if it's random 3D, it's 1/5 for 3D isotropic. And this was done by doing experiments and calculations as well. There is, in mechanical engineering, there's a separate course, which I think is a tech elective in composites that's offered. I don't know who's teaching that course. I've never taught composites before, but I can tell you that composites are part of this class, and they're also covered in applied elasticity graduate course, and I think maybe a little bit in mechanics of materials. Do you remember what transverse shear is? If you've taken mechanics. And those of you who are taking mechanics, we already covered it. Transverse shear in bending. So put your hands together. And then if you start bending it like this, you see, if your hands are not glued, this is what you're doing. Mechanically, this is equivalent as this. Try it. Okay. So for bending, when you take something and you bend it, the neutral surface does not deform, meaning its length stays the same, whereas here it becomes longer and here it becomes shorter. Okay. So we spend like the whole chapter in mechanics talking about that there's zero normal stress on the neutral axis, but in fact there is maximum shear stress on that interface. This is why over here the parameter is the shear strength tau sub c. Let's estimate the strength equation when the length is greater than the critical. And here's an equation for that, for fiber reinforced composites. And if the length is later than the critical length, then this would be an equation for determining the strength. This is important because that would allow you to make a calculation of the critical length of the fiber for it to be effective. And basically, like this little tiny lecture today covers the whole course in composites, where you get a combination of two properties, the elastic and strength-wise. How do you make composites? Pultrusion. Here's an example where the fibers are supplied and they are pushed through the resin impregnation tank. So they get soaked in rubber. And then they go through the free-forming die, curing die, and through the rollers. That's how the fibers get embedded into the matrix of the resin. Where you can also put them in the desired shape. The resin needs to be cured. Typically there's some sort of a heater somewhere. Another example is filament winding. And here you see helical, circumferential, or polar winding, where there's a cylinder and those fibers are wound onto the structure in a certain pattern. And then the matrix is typically applied in some sort of a liquid form. And then after this whole thing is, the mandrel is removed once you have this pattern, and you soak it in, and then you remove the mandrel itself. Who controls this? Who makes the machine? Well, somebody does, and you are the process engineer that does the manufacturing part. Structural. Structural means macroscopic. If you go to IKEA and you buy a table or you buy a tabletop, see, this is solid, and this is solid, and this is solid. But most of the tabletops nowadays are hollow. There's a top layer and there's a bottom layer, and they're made in a very similar way cardboard is made. Every time you get a package from Amazon, it comes in a cardboard box. What is the advantage of that cardboard box? What does it do for you? It protects the content of your parcel. At the same time, it's very stiff mechanically. And the third one, it doesn't weigh much. so its density is very small. The laminates are stuck in bonded fiber reinforced sheets, and typically they're stacked at 0 and 90 degrees. Now this is still bulk. The advantage is that you get in-plane stiffness in both directions. But the sandwich panels are have honeycomb pieces in between of the two facing sheets. This is the honeycomb structure. And there's a reason why the beehives are having the honeycomb structure, because this is the highest stiffness that you can get. And for this, you get very large bending stiffness and low density. And that's exactly how the cardboard is made. 2 sheet layers, glue, and the honeycomb. Okay. Composite matrix, ceramic matrix composites. This is particle reinforced, this is unreinforced, and this is fiber reinforced. Force versus bending displacement. What do you see here based on the data? If you just simply add particles that are spread, you can increase the modulus. So the stiffness is higher here, but the strain, or here in terms of the bending displacement, these materials are brittle. You add the fiber, you take it to the higher level of strain before it completely fractures. Metal matrix composites. This is 6061 aluminum. This is 6061 aluminum with silicon carbide whiskers. You can see that this is in terms of the strain rate versus the stress. You get higher slope for the curve. And here's an example of polymer matrix composites, elastic modulus versus density. Polymers, metals and alloys, and ceramics. So you see polymers are here, low elastic modulus. You combine this with some sort of reinforcement, and you're pushing this whole class of materials to a higher performance that can outperform metals and ceramics almost, in terms of the ratio of the elastic modulus to the density. So this is a very important slide that summarizes the idea of reinforcement of the composites, depending on what kind of matrix it is. And now you know the downfalls of metals, or the weak points of ceramics, and the weak points of the polymers. And the idea is to put their reinforcement in terms of the fibers and in terms of the particles to improve those weak points of either the metals or polymers or ceramics. There's always a trade-off between making something soft versus making something hard. Make something soft, you increase the fracture toughness, and it's better for processing. You make something hard, and you make it more brittle. So as a process engineer, this is always a battle of what you're trying to achieve in terms of this process to improve the product. I'll see you Thursday.